Welcome to today's Explainer. I'm so excited we're diving into this one because we're going to look at something that literally flips our everyday common sense completely upside down. We're getting into the nitty-gritty of chemical separation, specifically how we go about isolating massive, bulky macromolecules from really complex mixtures. It's a technique that's absolutely irreplaceable in both biological research and industrial manufacturing. So get ready, because this concept is as brilliant as it is completely counterintuitive.
Okay, so here's the fundamental problem to chew on. How exactly do you separate a massive biological polymer from a tiny little molecule? Like, if you picture a coffee filter or a sieve in your kitchen, your physical intuition probably screams that the big stuff gets stuck in the net, right? And the tiny stuff just slips right through? Well, that makes perfect sense in our macro world. But down in the microscopic realm of analytical chemistry, if you rely on that everyday logic, you're gonna get the results entirely backward. To solve this, we actually have to look at a highly specific type of separation where the rules of the race are totally flipped.
I absolutely love how the textbook explains this because it gives us the perfect mental model for what is actually happening. It compares molecules to vehicles and the microscopic pores of our filter to a city's traffic network. It says, and I quote, "Trucks using the bypass around the city can move faster than cars using the smallest streets in the city." I mean, just think about that for a second. The massive 18-wheelers, which are large macromolecules, they don't even try to navigate the tiny congested alleyways. They're like VIPs. They don't have time for local traffic, so they just take the highway straight around the whole shebang.
This traffic analogy plays out perfectly when you look at the stationary phase particles. Imagine these porous beads, usually made of organic polymers or silica, packed into a column. As the sample flows down, those big, bulky truck molecules are simply way too massive to enter the little pores in the beads. So what do? They wash right down the interstitial space between the beads. They bypass the city entirely. Meanwhile, the tiny car molecules are small enough to wander into the intricate winding maze inside every single bead. They get hopelessly delayed, taking every single side street. So in this weird microscopic race, the biggest competitors actually cross the finish line first. No way, right? But it's true.
And that brings us to the formal name for what we're talking about: size exclusion chromatography, or SEC. It's defined as a separation process where migration velocity depends on molecular size, causing the larger molecules to elute or exit the column faster than the smaller ones. Because of this really unique size advantage, SEC is an irreplaceable tool for analyzing natural or synthetic macromolecules. Now, it's not the most efficient process if you're trying to separate tiny intermediate molecules, but if you need to separate compounds with vastly different masses, like, say, stripping small contaminants out of a giant protein, SEC is absolutely the tool for the job.
So we've got the visual concept down. Now let's break down the actual math of elution volume. Because to predict exactly when a specific molecule is going to exit the column, we have to split the liquid into a couple of distinct zones.
The star of the show here is a little variable called K, which is the diffusion coefficient. It basically represents the degree of penetration into the pores. Let's look at the three states. First, if you're a massive molecule, your diameter is bigger than the pore. You are completely excluded from the gel. Your penetration is a big fat 0, so K equals 0. Second state, if you're a mid-sized molecule, you can enter some pores but maybe not all of them, so your K is sitting somewhere between 0 and 1. And the third state, if you're a tiny molecule, you have total access to every single pore in the stationary phase. You are fully permeated, meaning your K equals exactly 1.
What's truly fascinating is how those K values directly create the elution profile. The underlying equation is beautiful in its simplicity. Your total elution volume, which we call VR, or sometimes VE in the literature, equals VI, which is the volume of the interstitial space outside the beads, plus K times VP, the volume inside the pores. Think about the biggest molecule. Its K is 0, right? So that whole second half of the equation just vanishes. It elutes right at VI. But the smallest molecule, its K is 1. It has to travel through the outside volume and the inside volume, so it elutes way later at VI plus VP. This simple equation flawlessly dictates the boundaries of the entire separation process.
All right, so we understand the physical mechanism and the math. But how do we actually apply this in the real world? Well, SC goes by a couple of different aliases depending on the exact chemistry of the liquid you're using to push your sample through. Broadly speaking, the technique is split into two main camps: gel filtration and gel permeation.
It really all comes down to what you're trying to dissolve. If you're working with biological polymers, think proteins or polysaccharides like starch, you're going to use gel filtration.
In this setup, your mobile phase is aqueous, meaning it's water or salt-based, and you pair it with hydrophilic or water-loving stationary phase gels. But on the flip side, what if you're an industrial chemist working with synthetic polymers like plastics? You use gel permeation chromatography, or GPC. Here, your sample isn't going to dissolve in water. You have to use an organic mobile phase like tetrahydrofuran or chloroform and pair it with a lipophilic stationary phase like a styrene divinyl benzene gel. It's the exact same core physics, just applied in entirely different chemical environments.
Now, regardless of the specific method, you can't just pick a column at random. You have to map the specific pore size of your gel to the exact molecular mass range you want to separate. Different gels with varying pore diameters measured in angstroms have these highly specific sweet spots for optimal separation. And here is a crucial takeaway for calibration. You must use standards of the exact same polymer geometry. Why? Because macromolecules can be shaped like tight little pellets, or they can be long, stringy threads. Even with the exact same mass, a thread and a pellet are going to navigate our microscopic city traffic very differently. Oh, and a quick pro tip from the literature. If you need to expand your range of separation beyond what a single gel can handle, chemists will routinely link 2 or 3 columns together in a series to get the job done.
Let's take a step back and look at the industrial reality of this technique. What's the main takeaway? Well, size exclusion chromatography is basically a superpower. It's exceptionally good at separating compounds with vastly different masses. That makes it absolutely indispensable for quality control of commercial polymers or isolating natural macromolecules. But we do have to respect its boundaries. The column efficiency in SE is honestly far from ideal. If you're trying to separate a bunch of very small intermediate molecules with similar sizes, SE is just not the right tool for the job. And as we just mentioned, you always have to be careful that your calibration standards perfectly match the physical geometry of your sample.
Which brings us to our final thought. The next time you think about filtering or separating the large from the small, I want you to remember that microscopic traffic analogy. Ask yourself, does your mental model need a total reversal? Because in the winding maze of size exclusion chromatography, the biggest molecules don't get trapped. They hit the bypass and win the race every single time. It's a truly brilliant paradox that makes modern macromolecular chemistry possible. Thank you so much for joining me for this explainer. Keep questioning your everyday intuition, and I'll catch you next time.